Hello everyone today. The object of our research is MLOps process under resource constraints and the impact of various types of disturbance on the AI system. The subject of the research are the architecture of the MLOps and methods of ensuring the resilience of AI system with limited resources to various types of disturbing influences. The goal is to develop a new MLOps methodology that ensures the resilience of resource-constrained AI system to such negative factors as adversarial attacks, fault injections, drift, and out-of-distribution data. Rapid progress in AI technologies increases uncertainty about the level of AI resilience and its safety with respect to various kinds of disturbances and intrusions. Disruptions to this AI system can have negative impact on the health, mortality, human rights, and assets values. The main AI system threats include drift, adversarial attacks, and faults. Each of three types has subtypes depending on their way of formation and specifics of impact. The corresponding disturbances may differ in time characteristics of their occurrence, and different variants of their mixing are possible. The vast majority of researchers consider each type of disturbance for AI systems separately, and the questions of compatibility of methods for ensuring resilience to each of these disturbances remains under-researched. So our research focuses on MLOps methodology to ensure resilience to different types of disturbances during the AI system lifecycle. Conventional MLOps approaches in the context of resource-constrained systems focus on applying AI model compression methods before deploying them. The issue of ensuring the robustness and quick adaptation of AI system to changes and disturbances in conditions of constrained resources is still less studied from the MLOps perspective. The systematization and effective combination of AI defense methods is a separate complex area of responsibility, as the number of sources of disturbances, attacks, and defense methods is constantly growing. Important principles in MLOps are separation of responsibilities and collaboration between teams. New MLOps stages for ensuring resilience aspects should be implemented as post-hoc procedure to maximize the separation of responsibilities. Illustrated diagram of the proposed resilience via MLOps additionally includes the stages of post-hoc resilience optimization, post-hoc uncertainty calibration, uncertainty monitoring, test time adaptation, and graceful degradation. At the stage of resilience optimization, it is proposed to attach computationally efficient adapter or meta-adapters to the original model in order to increase robustness and speed of the fine-tuning process. If the base model is given and adapters and meta-adapters of specified architecture are connected, then it is necessary to tune the meta-adapters in such way as to maximize the average value of the resilience indicator. Since the main objective of AI training is to maximize validation metrics, or minimizing their proxies in the form of loss function, the task of increasing resilience to disturbances is an additional high-level task. Therefore, using the ideas and methods of meta-learning to maximize resilience seems to be the most logical and promising approach. In this case, the process of generating disturbances and adapting to them happens in the internal loop of meta-learning. The gradient of resilience indicator and its optimization are performed in external loop. As integral indicator of resilience, it is proposed to use the normalized sum of the validation metric values over T adaptation steps. In order to normalize this sum, we divide it by the number of adaptation steps and the validation metric values taken before the perturbation. Maximizing this criterion during meta-learning will increase the robustness and efficiency of adaptation in the few-shot learning setting. To estimate the resilience gradient or meta-gradient, we propose the following approach. First, generating a version of the adapter and meta-adapter weights by adding and subtracting the generated search perturbation vector. Secondly, running the procedure of adapting the obtained weights to each implementation of external disturbances. And finally, Gaussian smoothing of the difference in the resilience criterion on both versions of the perturbed weights on the sample of external disturbances. This slide illustrates the pseudocode of the meta-learning procedure for resilience optimization. The post-hoc calibration algorithm requires adding certain add-ons to the frozen model that are adjusted on the calibration data to reduce the discrepancy between prediction confidence and the actual probability. Bayesian binning into quartiles was chosen as calibration add-ons for classification model. Unexpected changes in the domain of other distributional shifts can always occur. Promising approach to mitigate such disturbances is to use the ideas and methods of test time augmentation and test time adaptation. It is proposed to calculate the entropy of the marginal probability at the model output for its tuning over a certain number of iterations for low confidence predictions. If after tuning, the entropy at the model output does not exceed the threshold values, it is necessary to switch to the graceful degradation mode. The easiest way to use graceful degradation is to hand over control to a human to fine-tune the system on labeled samples. CFR10 dataset contains training and test subsamples. To simplify the experiments and analyze the results, we will divide test set into 4 parts. Each part of the test data is needed to simulate a part of the AI model's life cycle. Several configurations will be considered to illustrate the impact of additional stages of resilience via MLOps on the accuracy and speed of recovery. Config 0 is a conventional MLOps with the fine-tuning stage and active learning feedback loop. Config 1 it is upgraded config 0 with resilience optimization stage. Config 2 is upgraded config 1 with predictive uncertainty calibration stage. And finally, config 3 it is upgraded config 2 with test time adaptation stage. According to table 1, the use of post hoc resilience optimization increased robustness to the fault injection by 5%. Moreover, tuning on 10% of the test data increased robustness to fault injection by 6%. Post hoc uncertainty calibration increases the robustness of fault injection models by average of 4.4%. Test time adaptation increased robustness to fault injection by 6.9%. Similarly, according to table 2, the use of post hoc resilience optimization increased robustness to adversarial attack by 7%. Moreover, tuning on 10% of the test data increased robustness to adversarial attacks by 7.1%. Post hoc uncertainty calibration increases the robustness to adversarial attacks by average of 1.3%. Test time adaptation increases robustness to adversarial attack by 4.72%. Even an increase in the intensity of attacks does not lead to noticeable decrease in accuracy. In addition, the use of post hoc resilience optimization increases the integral indicator of resilience to task change by 10.5%. This slide shows